Let me know that you can see the screen.
Yes, sir.
Good.
Yes, sir.
Yes, sir.
Good. Okay, let's have a quick recap of what we were doing in this unit 2. Started with the idea of probability, the conditional ones, the independent ones, in terms of the events, the total probability and Bayes theorem, and did a little bit about the combinatorics. We then jump to random variable, which is nothing but providing numerical outcome to the events in the sample space. And then we discuss that there can be two kind of random variables, discrete or continuous. And correspondingly, for probability, we have probability mass function for the discrete random variable, and of course the cumulative distribution function. And for the continuous random variable, we have probability density function, PDF, and the CDFs. Then we discuss some important properties of those distributions, the PMFs and the PDFs. For example, the expectation value of the random variable, variance of the random variable, which we also call as sigma square, and then the standard deviation of the random variable, and other central tendencies like median and mode. And then we mentioned that those central tendencies and this spread around the mean, they are basically nothing but the algebraic moments and the central moments. So we start with the first and the second algebraic and the central moments respectively, which are mean and variances. And of course, we have some others just like skews. So we did ask this question, right? Skewness is what we did. And then there is the fourth standardized central movement. And that movement is called, so what is that movement called? The fourth standardized central movement?
Sir, kurtosis.
Kurtosis.
Kurtosis. And the kurtosis correspond to the peakness. I'm not going to dwell right now, but we may discuss it at some point of time when we are discussing the normal distribution. That normal distribution or the Gaussian distribution becomes one of the most important distributions in probability theory. And we try to define distributions with respect to normal distribution. So kurtosis, it is basically the way the peaks are with respect to the normal distribution, whether it is whether a distribution is as peaked as a normal distribution or not. That's what generally we are interested in. And then basically coming to some important PMFs and the PDFs, the probability mass functions for the discrete ones. We started with binomial distribution. So here is what we were discussing about the binomial distribution. So this is one of the first distribution with which we started. We are interested in discussing about a distribution where we define a random variable to be number of successes in fixed trials, and which we are putting as n. And each of the trial can result in only one of the two disjoint outcomes, success or failure, we are defining. And then the probability of success in a given trial, that is also fixed, is given by small p. So two parameters are fixed, n, the number of trials, and the probability of success in each trial. Of course, that fixes the probability of the failure as well to 1 minus p. And we consider that trials are all independent and identical. Now, this random variable is a discrete random variable because we are talking about number of successes. So you can have 0 success in n trials, 1 success in n trial, 2 success in n trials. And what is the maximum number of successes in these trials? The maximum number of successes will be n, right? So we are interested in writing PMF or PDF for the binomial distribution. PMF or PDF?
Sir, PMF.
PMF.
PMF, because X is a discrete random variable, absolutely right. So we are interested in writing a PMF, but interestingly, one additional thing which comes here, that we will be able to write this PMF only if these two, N and P, are defined to us. where n is the number of trials which is fixed and p is the probability of success in each trial. These kind of items, they are called parameters. So I will come to that, but please see that in this distribution we have one random variable which is the number of successes in n trials. N and p have to be given here. So it's a very common way of writing PMF as px semicolon n comma p, where after semicolon I am writing the parameters of that distribution. So I will say a little bit more on that soon, but we have to write it. So how to write? Now tell me, x is a random variable such that small x is the number of successes in n trials with small p is the probability of success in each trial. So let's say x successes. So maybe these are x successes and rest are failures. So n minus x failures. So how to write this probability? If we have x successes each with probability p and n minus x failures each with probability 1 minus p.
Sir, we can use combination.
So what will be used? So let's say probability of success will be p and the probability of the success in the next event is also p. Let's say, I mean, it's just one of the case. So that in x successes we have probabilities, and since these events are all independent, so the total probability will be nothing but p raised to power x, right? What about the failures? So 1 minus p. So how many failures? 1 minus
And
p
N
n
minus
minus
x.
x.
n
So
minus x.
of course we have this quantity which will surely come in, that p successes and n minus x failures. So is this the probability mass function? Does this make sense or something else?
Sir, NCX also.
Okay, let me write ncx. And why did you write ncx? N is capital, so let me just write it. Yeah, why did you ask me to write this ncx?
Sir, because it is the combination of X trials in X successes in N trials.
Yes, the important point to see is good. The important point to see is that we have x successes defined and n minus x failures defined, but it does not mean that which of the n trials lead in successes. So this could also be like SF, SSSF, and or SSFSS, so on and so forth. So there can be many ways, and this combinatorics is included in this term n combination x, and which is n factorial divided by x factorial and n minus x factorial. Remember this binomial coefficient. This just tells us, I should also write this as capital N. So this just tells us that these permutations among x and permutation among n minus x, of course, are divided by, but the whole factor has to come to tell us that it can be in any of those x trials we are getting successes and any of n minus x trials we are getting failures. That's why combinatorics is very important. But once you have defined this, so we do need to say that x of course can take values 0, 1, 2, so on and so forth up to capital N, right? Small p, it's a probability of success in each event, so it has to be between 0 and 1, and capital N of course at least greater than equal to 1. At least we are talking about at least one trial, right, in the experiment. So it's equally important to understand if there are constraints on the random variable and the parameter. The constraints on the random variable is just that it is a discrete number going from 0 to capital N. And this probability we can write 0 otherwise to explicitly mention that if somebody wants to ask any question of probability anywhere else, then this is going to 0. Now I did mention that binomial distribution applies to any place where there are two outcomes and probability per outcome is same. And I also mentioned that in radioactive decays, this happens very commonly. And we will still have to answer that why we use the Poisson distribution, but that comes next. So this is how the PMF is written. Now, once the PMF is written for a particular distribution, we can ask to figure out anything related with that in terms of the algebraic or the central movements. The ones which are very important, of course, let's just try to figure out. This is expectation value of x. Before doing that, can somebody tell me if this Px is properly normalized or not? Remember, your PMF is supposed to be normalized. Is this Px normalized? What is the normalizing condition? Summation of Px has to be equal to 1, right? Where x is starting from 0 and should go up to capital N. So let me just write down x equal to 0 to n ncx px 1 minus p n minus x. Is this quantity equal to 1? So how to check that? For that, you have to just remember that if there exist, let's say a plus b, two monomials n raised to power, then this can be written as x is equal to 0 to n ncx a raised to power x, b raised to power n minus x. This is what we call as the binomial expansion for two variables a plus b raised to power n. Yeah, I mean, of course, you can expand it nc0, a0, b n minus 0, and up to ncn. So this is what we'll have to remember. If you remember this guy, because of which this ncx is called the binomial coefficient, by the way, this is the binomial expansion and the coefficient ncx's are called binomial coefficients. So if you remember that, can you write down this ncx px 1 minus p n minus x in the manner in which I have written this a plus b? What will?
1.
So this becomes p, which is our a, and then 1 minus p, which becomes our b. So this guy becomes a, this guy becomes b raised to power capital N, which is 1 raised to power capital N. And since n can take only value greater than equal to 1, the only result will be 1. So PMF is properly normalized in the case of binomial distribution. So this qualifies NCX PX 1 minus P n minus X qualifies to be a PMF. Of course, rest of the things you can check whether it's a positive one, whether it lies between 0 and 1. That of course it will hold true. Okay. So now find out the expectation value. So what are the questions which are asked? Once the PMF is given, find out the expectation value, find out the variances, and maybe the skewness and the cutoffs, so on and so forth. So we will try to find out the expectation value of the random variable, which is same as the mean. The mean of a binomial distribution. Have you done this problem ever? I mean, or we are doing it for the first time?
No, sir.
You never did it. Okay, so let's just try to do that. So expectation value of x for the discrete variable. How do we define it?
So take the sum and divide by the n into x, number of repetition.
X times
Probability.
Probability. Yes.
probability,
Probably.
where x is from 0 to n. So let's just write it down explicitly. So x is equal to 0 to n, and then x n factorial x factorial n minus x factorial p raised to power x 1 minus p raised to power n minus x. So this is the starting point. Now, please look into it, what I am going to write, and then let me know if you understand this one. So, first quantity is x multiplied by px, and x will take the value 0. So, I can of course write down from x equal to 1 to n factorial, x minus 1 factorial, n minus x factorial, p raised to power x, 1 minus p, n minus x. Fine, because the first, anyway, I mean, one way or other you have seen it. Since x, we are taking the expectation value. So if you write down the first term where x is 0 times some probability, which can be 0 or 1, between 0 and 1. So that term will contribute only 0. So it is equivalent to writing from x equal to 1 to n, and then what? I have just x minus 1 factorial, because okay, I have x in the numerator, so I have written in the denominator x factorial as x minus 1 factorial. That makes pretty simple. Next is something which is little bit tricky, but once you understand it, then it will be clear. So all the terms of x's and n's, I am going to write in terms of n minus 1 and x minus 1. Can I write n factorial as n minus 1 factorial?
Then multiply by n also.
Multiply by
Yes,
n,
sir, and
right?
multiplied.
Absolutely right. And that means, okay, x minus 1 factorial. And then look into the denominator, n minus 1 minus x plus 1 factorial. Mine I added and subtracted 1. I am writing p raised to power x as p into px minus 1. 1 minus p raised to power n minus 1 minus x plus 1. So all I did a little bit of the rearrangement of terms, so that I am writing x minus 1s and n minus 1s. Why I am doing it, it will be pretty clear to you soon. But let's just define y is equal to x minus 1 and n prime is equal to n minus 1. So what am I doing? I am taking capital N and small p outside. So I took small p out, I take a small n out. N prime factorial divided by y factorial, n prime minus y factorial, p raised to power y, 1 minus p raised to power n prime minus y. And what is the summation starting from? Y is equal to, y is defined as x minus 1.
0
0.
n
0
minus
to
0.
2,
n minus 1
N minus 1.
which is nothing but n prime.
n prime.
Yeah. So now see what I have done. I have written n p, and this term. What is this term?
1.
How?
1.
This
Because that
term
is the
will be,
that is the
this term will be p plus 1 minus p raised to power n prime. Please look into it. What I have done, basically n prime factorial over y factorial, n prime minus y factorial is nothing, just what you are saying. It is n prime cy py 1 minus p n prime minus y. So this is the reason why I have written everything in terms of n into n minus 1 and x into x minus 1. Wherever n was coming, I was converting to n minus 1, and wherever x was coming, I was converting to x minus 1, so that I basically use the property of the binomial expansion. And this guy, this is what you are saying, since n was greater than equal to 1, at least one trial, so this n prime should be greater than equal to 0. 1 raised to power 0 or greater than equal to that quantity will always be equal to 1, and hence the expectation value or the mean of the binomial distribution turns out to be nothing but the total number of trials times the probability of success in each trial. So this is how one gets the expectation value of a binomial distribution. Now, if I ask you to now find out the variance of the binomial distribution. So how the variance was defined? It can be ex square minus, you may need to go back to look into the notes. We wrote it as ex minus mu square expectation
Sir,
value, or in this manner. Yes, please go ahead.
sir, in the previous page, you have written x equals to summation x is equals to 1 to n.
Yes.
Sir, in the second line. So, sir, how it
Yes.
is changing from x is equal to
Oh,
0 to 1?
because I mean, that is clear from the definition itself. Look at the definition of expectation value of x. X times px, right? And px is between 0 and 1, right?
Yes,
Yes.
sir.
So if you expand the term, what will be the first term? What will be the first term? So 0 times p of 0 plus x equal to 1 times n xpx, right?
Yes, sir.
So this term, the x equal to 0 term, is not going to contribute anything, right?
Okay, sir. Got it.
So that is what we have done. Yeah, that's where I mean, this is, since binomial distribution is important, so we are doing this. But I agree that this looks like a trick. This trick is applicable in variety of distribution. We are going to see. We are going to do the Poisson and the, of course, binomial. But if you go into the books, find out for the negative binomial distribution, hypergeometric distributions, you will find that this trick will be used. However, the trick, of course, is not exactly a trick, because you know that your random variable is starting from the value 0, and whenever you start with the value 0, the first term, the 0th term, is not going to contribute. So that's all it means. But yeah, I mean, let me just give you a hint, and then you will have to see how to proceed. I need to figure out that you can do this problem. So how to do this variance of x, expectation x square minus ex square? We have already got this mean on the previous page, which is nothing but n times p. What we want to do is to take care of this term, but we cannot directly take care of this term in the binomial distribution. What we can take care of is, as you will see, ex into x minus 1 kind of a term. So we will be able to do the variance x, but the term which we will be doing using the same trick, what we have used in the previous page, is this one. So now how can I write ex into x minus 1? This is nothing but ex square minus x, which is nothing but e of x square minus ex. So put this guy back in our variance equation. Your variance equation becomes then e of x into x minus 1 plus e of x minus e of x whole square. And we have already got second and third term on the previous page. We are interested in getting the term expectation value of x into x minus 1. Why this kind of a term? You will see the reason soon. So if I write x into x minus 1, how this will be defined? Summation x going from 0 to n, then
X
x
into x
into
minus
x minus 1 px. Now, how can I write this guy? This guy will be 0 for x equal to 0 and also 0 for x is equal to 1. So I can directly write from x equal to 2, just follow the previous page, n factorial x minus 2 factorial n minus x factorial p raised to power x n, sorry, 1 minus p raised to power 1 minus p raised to power n minus x. Let me just go back to the previous page. Please see what did I do last time. We started with x into n factorial over x factorial, so on and so forth. And then in the second line, we basically took care of it by writing the summation from x equal to 1 to n. This time it is from x equal to 2 to n. And denominator, since we had x factorial, so we have written x factorial as, so just remembering that we have written x factorial as x into x minus 1 into x minus 2 factorial. And of course you can write it. So any questions on this point? No. I will now request you to do the same thing which we did last time and just go ahead, solve it. So what did we do last time? We wrote everything. I have not written the summation n properly. Okay. So this should be n minus 2 factorial. Can I write down that? No, I should be doing n into n minus 1 divide by x minus 2 factorial, and then n minus 2 minus x plus 2 factorial p raised to power x minus 2, which means what will go out? P into p, yeah, p square, absolutely right. And then 1 minus p raised to power n minus 2 minus x plus 2. So what have I taken out? N into n minus 1, p square is out, and then rest of the things. Y should be from 0 to n double prime, where what is my y? It is x minus 2. And what is my n double prime? It is n minus 2. And you see, I can write down C y p y p raised to power x minus 2 1 minus p n double prime minus y. And again you are going to do the same thing. What happens to this summation?
This will be equal to 1.
This is equal to 1, and this becomes n minus 1 times p square. So you got the first term of the variance. You already got expectation value of x, which is n times p. Put these terms back and get the result for variance. So let me know what is the value which you are getting. So n into n minus 1 p square plus np minus n square p square. What is the result?
So NP into 1 minus P.
N into P 1 minus, yeah, NPQ. I am avoiding writing
NPQ.
Q, although you can, yes. So you have all got this NP into 1 minus P?
Yes, sir.
Yes, sir. Okay. So
Yes, sir.
this is how we get the variance of the binomial distribution. I understand that it may take a little bit of the time in order to understand that what we have done, but please see the whole idea comes from the fact that the terms, the factorials are written in terms of the successive numbers multiplication. So n factorial is n into n minus 1 into n minus 2 into n minus 3 factorial, so on and so forth. So if we ask you to go for the next movement, then most likely what you are going to do in that case is that you are going to write e or expectation value of x into x minus 1 into x minus 2. And you will be able to follow the same steps what you have followed here. So in the case of binomial distribution, if one tries or one wishes to go for finding out the higher moments, it is written in terms of e x into x minus 1 into x minus 2, so on and so forth, so that one utilizes the important point which is coming from the summation of the whole binomial coefficient is going to give you 1. Now I can also ask you to give me the standard deviation. So what will be the standard deviation? Which is positive square root of variance. So this becomes NP1 minus P. So the two results, that mu is equal to NP and that sigma becomes NP1 minus P, become very important. These are the results which are generally asked when the binomial distribution is asked. Of course, along with your PMF, the one which you have drawn. Once you write down the PMF, you can get the information about it. Now, at this point of time, I would also like to remind you, in quantum mechanics, we write a quantity something like, okay, let me just write. So this comes, that a Hamiltonian operator acting on its eigenfunction gives the energy times that function back. So H psi acting on psi gives E psi, and I take this from the left hand side. So I put the bracket, which means the inner product of this one. This is several books, of course, also written as in this manner. Yeah, this is what we call as the expectation value of the energy. Can somebody tell me what is this? In quantum mechanics, when we use this. So if I want to make a measurement, what does this quantity signify?
So the probability that we'll get that that measurement, that state when we make a measurement.
Yeah, but
That
that
energy.
was not taking the inner product from the left hand side. If you remember, that was something like this, that H psi gives you E psi, something like this. This is what you are putting as the eigenvalue equation. And I can ask you a question, very general question, that what is, let's say, this guy, where of course skies can be expanded in terms of the size.
So
So
it's
what
mean.
this is,
Average value of
mean
energy.
or
Average value.
expectation value. Now please understand the meaning of this. It means that if I have identical and indistinguishable states like chi's, several of these makes, and I take this measurement H on this one, then what will be the average value which will be coming out by doing plenty of measurements of H on identically and indistinguishably made states chi's. So this guy, chi h chi x or psi h psi, this is nothing but the expectation value or the mean. And in fact, if you remember, if psi is the position wave function, then you are doing something like this: psi star h psi, let's say, okay, in position wave function, so d cube x. So when you are doing this, you are finding out nothing but the expectation value or the mean. You can be asked to find out that of the kinetic energy operator, the potential energy operator, the momentum itself, or so on and so forth. What you are doing there is finding out a quantity which is nothing but finding out the expectation value of a probability distribution. That probability distribution can be a mass function or, of course, the density function. So in the additional class today, which we are going to take at 2 p.m. today, I will do one problem which you might have done in the past, but we will still do it to correlate it with what we are doing currently. That I will just take one quantum mechanics problem and we'll solve it there in that class. Fine. So Binomial distribution, this mean and the standard deviation. We now go to the next distribution called Poisson. And by the way, you can try to find out skewness and kurtosis. All you will have to do in that case, you will have to use your knowledge of x into x minus 1 into x minus 2, relate it with x cube, things like that. This is what you will have to do. Now, Poisson distribution becomes interesting and useful as you have told me that you are using this distribution in the counting statistics, and I still have to answer one question, that why we use this Poisson distribution. So, what is Poisson distribution? Actually, Poisson distribution is in one sense, it is a limiting form of binomial distribution. When I say limiting form of binomial distribution, what it means is that in the case of binomial distribution, we were considering n trials and small p, the probability of the success in each trial. Yeah. So let's consider even we are doing n trials, but such that n is very, very large. So I can write down this at tends to infinity. And such that the probability of success in each trial, this is very small. So that this n times p. Now you look into it. Trials being very large, probability of success in each trial being very small, yet the NP is a small finite number. So NP is still a small finite number because n is very large and p is very small. So in such a case, we can use a distribution what we call as the Poisson distribution, which gives us the probability of occurrence of a certain event. So it is very similar to binomial distribution, except that we are talking about very, very large number of trials and the probability of success in each trial being very, very small, such that capital N times P is a small a finite number. So Poisson distribution doesn't deal with something which is very different from the binomial. It is something very similar to binomial. In this case, we can define a quantity called lambda, so that the PMF, probability mass function, for the number of occurrences or the number of successes can be written as a constant times, anybody remembering the distribution?
Hello?
Yes.
Sir, the distribution is e raised to power minus lambda into lambda to power k upon k lambda.
Lambda
We
to
can
power.
take x, k is the random variable.
Okay, so what I am taking right now, remember the random variable is a numerical one, so I am taking x. Fine. So x can take value now, number of occurrences 0, 1, 2, 3, 2, up to what? How many trials?
Infinity.
Infinite.
Infinity. Right. So infinite trials. This lambda will always be greater than 0. This is a new quantity which I have defined. But interestingly, if you look at the form of the PMF, x is the random variable. What is this lambda then? So there is one called random variable and another quantity after semicolon is called
Parameter.
parameter. Unless until parameter is defined for a given problem, you can see that you cannot find out the PMF. The PMF is completely defined by using two important items. One is called the random variable, which is what we are saying that may vary. There may be one success, there may be two successes, three successes, so on and so forth. But then the other quantity which we call as the parameter, that has to be fixed. In the case of Poisson distribution, it is a one parameter distribution. In the case of binomial, how many parameters were there?
2.
There were two parameters which are there, capital N and small p. Now we will exactly follow what we did in the case of binomial distribution to find out the mean, the variances, so on and so forth. But first, what is this k? Somebody already told me what this k is.
E raised to power minus lambda.
E raised to, and how do you get that? K is what we call as the normalization constant of a distribution, and we can find it out pretty quickly. How will we find out the normalization constant or coefficient?
Sum the
You'll take the
probability and
summation
equal to 1.
Absolutely right. So you write Px, x in this case going from 0 to infinity to 1, and you should be able to find it. Where Px, it's a shorthand notation of writing the same thing. So probability mass function completely defined, one random variable and the parameters are given, and it is given like this. So let's just do that. What will happen in this case? So k lambda x x factorial equal to 1, where x is going from 0 to infinity. Now k is a constant. Of course, I can take out lambda x x factorial. So what is this guy?
E to the power minus lambda.
E raised to power minus lambda or e raised to power plus lambda?
So e to the power lambda.
E
Plus
to
lambda.
power lambda. Please
Plus
see,
lambda,
and
sir.
there this is why you are doing everything here at the MSc level, that we need your knowledge of the BSc. When I am writing a series like this, x equal to 0 to infinity lambda x over x factorial, you can see that it is nothing but 1 plus lambda square over 2 factorial plus lambda cube over 3 factorial plus so on and so forth up to the infinite terms. So you write lambda nth term, but we are not even stopping there. It is up to infinity. This is what the form which we know for exponential series. If you truncate it to nth term, of course, in that case, it is not the whole exponential lambda. Truncation is not allowed here. So you have to go up to n tends to infinity terms. But once you understand it, it is k times e raised to power lambda is equal to 1. So what is k? This is e minus lambda. So this guy, which I gave as the constant, that is found from a normalization 1. E raised to power minus lambda is nothing but the normalization constant of this PMF. And hence the PMF, the final PMF after taking care of the normalization coefficient, becomes e raised to power minus lambda, lambda raised to power x over x factorial, where x, of course, going from 0, 1, 2 to infinity, lambda is greater than 0. So this is the PMF of our Poisson distribution. Next thing, let's find
Sir,
out.
could you please explain how it is of this form lambda to the power x divided by x factorial?
At this point, I am not doing it, but I can show it that what happens if the binomial distribution, remember those factorials which we are using? Let me just tell you. Yeah, I can do that, but it is at this point of time I'm not, but I will give something. See, n factorial over x factorial, n minus x factorial. When you go for n tends to infinity, how do you take care of factorial terms? If there is something like n factorial, and if I go for n tends to infinity, how do you write down the factorial form? Do you know that?
Gamma
No, sir.
function.
No, it's not gamma function. Yeah, okay, what you are saying is something simple. What you are saying is that there exists something like gamma n plus 1. which is written as n factorial, right? I mean, this is what you are saying. So what happens to n factorial when limit n tends to infinity? And this is why I am not right now immediately doing it, because I do not want to digress you, but it's a very famous one which you use in your statistical mechanics. If
That we
you
take it
can,
to the power something.
yes, you take it to the power, but if you did long back the famous
ln
Gibbs
minus n.
paradox, you did the Gibbs paradox, the Sacco-Tetrode equation. Did you know how did you resolve that problem? The Gibbs paradox, how did you resolve that? You must have heard the word Gibbs paradox, right, in statistical physics? Forget
Yes,
about
sir.
that, you remember
Yes,
it
sir.
only.
Yes, sir.
Okay, so
Yes,
there is
sir.
this famous problem which comes that you have the collection of classical particles and you are trying to figure out the entropy expression out of it, and then suddenly you will find that the ideal gas law will not be obeyed, or there is some term which is missing. Classical particles were always considered identical but distinguishable. So you took care of that by taking care of one term in the denominator, which you say that since the actual particles are indistinguishable, so you can divide the number of microstates by n factorial, and then you use a particular approximation to take care of very large number of particles. So n
Stirling
factorial,
approximation.
yeah,
So
right,
Stirling's approximation.
Stirling's approximation. So that Stirling's approximation comes for the rescue here also. It is the same Stirling approximation, which we use to show that the binomial expression can be reduced to simple expression like this Poisson one. Okay, so I may give it to you something, maybe I will just put something there and then we will discuss it. I will, I mean, write down something on a piece of page and then I'll upload that. But let's just do this, what I want to do in this class, which is the expectation value of the path. So it is exactly the same. And I will take your help to do this. X, Px, x is equal going from 0 to infinity. Fine. Now this guy, x times e minus lambda, lambda x factorial, x going from 0 to infinity. Can somebody help me out with this one? You have to follow the steps which you followed in the binomial one. So what should I do as the first step?
The summation goes from x equal minus
1 to
9, x is equal to infinity.
To 1 to
1 to
infinity. Okay, great. E raised to a minus lambda remains lambda x minus 1 times lambda. So this will become
and
lambda x, right?
x minus 1 factorial.
And x minus 1
x minus
factorial. So what are the things which can come out of this summation now? Lambda can come
E to the
out.
power
Lambda.
minus lambda
The
into
E
power
lambda.
minus lambda can come out. X equal to 1 to infinity lambda x minus 1 over x minus 1 factorial, which of course you can, if you want to do the change of variables so that it is easier for you to write down, lambda e minus lambda y is equal to 0, infinity minus 1 is still infinity, lambda raised to power y factorial. What is this guy?
E to the power lambda.
This guy becomes e to power lambda, which means that this guy, the whole of the guy will become lambda. So mu, expectation value of the random variable, pretty quickly becomes nothing but this parameter. So the parameter lambda, which was not clear what this parameter is nothing but the mean or the average value of that particular distribution called Poisson one. And I want to quickly ask you to also help me out with Ex minus 1 so that I can find out the variance also pretty quickly. So how to do exactly the same way? Now that you know the trick, x minus 1 px. So this will become what? X equal to 0 to infinity. For the sake of completeness, I would like to write it down. E minus lambda, lambda raised to power x, x factorial. I can take out wherever you have problem, you will just let me know. X is equal to 0 to infinity. Again, exactly in that. E raised to power minus lambda, I am not touching. Lambda square, lambda x minus 2, x minus 2 factorial. Fine. And this guy becomes lambda square e raised to power minus lambda out. And I can write down y is equal to 0 to infinity. Infinity will be unaffected by 2. And lambda raised to power y over y factorial. And this guy will again be exponential lambda. So can somebody help me with variance of x of the Poisson distribution now? So that will be first term, which comes ex x minus 1 lambda square plus expectation value of x, which is lambda minus expectation value square. And just to tell you that from where I did write that expression, of course, I mean, I used the expression which I already used earlier, which is this expectation value of x into x minus 1 plus expectation value minus expectation value of x square. So let's go back. And this is what I have written. The first term is what we have just now calculated, which is x minus 1 plus expectation value of x, which is coming from lambda, minus expectation value square, which is lambda square. So variance is also lambda. This is something very interesting about the Poisson distribution, that both the expectation value and the variance of this both turns out to be lambda. What will be the standard deviation?
Square root of lambda.
Root of
Root
lambda.
of lambda.
Now at this point of time, I will just ask you to recall what you have done in the counting statistics or in the GM counter experiment. So first question, the one which we haven't answered, why the nuclear decays are approximated by Poisson distribution and not the binomial distribution? In general, the decays, particularly the sources which you are using in the lab, they have a very long lifetime of the order of years, which means that the probability of decay of a nucleus in a given second or in a given minute is very, very small. And the collection of nuclei which you are considering is very large. Since you are considering a very large number of nuclei with the probability of decay in any given second or minute, which is basically the duration during which you are conducting your experiment, since that's very small, hence you are using Poisson approximation for the nuclear decays. It's not about whether we can find out the number of nuclei or not. It's not about whether we can find out the probability or not. It is because we have very large n and very small p. What additional advantage which Poisson distribution brings to the table? The additional advantage which it brings to the table, that we do need to know only one parameter lambda and nothing else. In the binomial case, we need to know two parameters, capital N and small p. In the case of Poisson distribution, we need to know only one parameter. Hence, Poisson is a nice approximation of the binomial. It is a one parameter distribution as opposed to the two parameter binomial distribution. So this is the reason. You know the lifetime, by the way, and you know the activity of your sample. So with these two known, you of course can find out everything regarding the binomial distribution as well. You can find out your probability of a decay. You can find out the total number of nuclei which are present in the source. Fine, but it is still calculation wise using single parameter as opposed to two parameters is simple, one. And two, since we have this point cleared up, that is P is very small and capital N is very large. Hence, we can use this Poisson distribution. So this is the reason why you use the Poisson distribution. Okay, this is point one. Point two. Now, in the counting statistics, what you are doing, that you are doing an experiment for, let's say, a given interval, maybe 2 minutes, maybe 3 minutes or something like that, and you get a number n, which is nothing but the counts. Now, what you do immediately afterwards, if I ask you what is the error or the uncertainty in this number, what is the number which you add to that?
The square root of it.
So you put square root of n, and from where this square root of n is coming?
The Poisson distribution.
Right. So what you are considering, that the number n which you have got, the counts which you have got in the 2 minutes duration, this is nothing but the lambda parameter of your Poisson. And remember, the lambda parameter of the Poisson is nothing but the mean itself of the Poisson. So you equate that number n by the mean of the distribution. And what is the error in the Poisson distribution? That is nothing but square root of lambda. This is what we have seen in the standard deviation problem. So look into this. Standard deviation of the random variable turns out to be square root of lambda. So this square root of the lambda is basically what is the. So you basically utilize the knowledge of the Poisson distribution, that mean is represented by lambda and the standard deviation is represented by square root of lambda. That is immediately converted to your knowledge, that in the 2 minutes time, whatever reading you have got is nothing but something as the mean of the Poisson distribution, and hence the uncertainty which you can account for in that is square root of n. So this is the reason why you are using n plus minus square root n in the case of your counting statistics. Remember, there are two things which are happening. One is that the nucleus is decaying. Another is that that particular decay results in some radiation which is interacting with the medium. So interaction of the radiation with the medium, which gives rise to count in the system. So counting comes only when that radiation interacts with your GM system. So this counting statistics experiment, what you are doing in your nuclear physics experiment, and some of you may do later on, this is a typical example of utilizing probability distribution in the case of detection. It's not about the decay only, it is about the interaction of that radiation with the system, which is also governed by Poisson distribution. So there are two places where we are using Poisson distribution here. One is that the decays themselves are reflected in terms of the Poisson distribution, and two is that the interaction of that radiation, whatever the gamma or the beta, with your Geiger-Müller counter, that is also reflected. This is what the counts are in the GM system. They are also reflected by the Poisson distribution. So the rest you can read in the Knoll's book. Of course, you may be using Glenn F. Knoll's book for or chapter 1 or 2 for this one. Okay, questions here? So if no questions, then what we have done in today's class, okay, this one, that we have taken care of two useful distributions. We wrote down the PMF. One question which I haven't yet answered, basically, that how the form of the Poisson distribution turns out to be lambda raised to power x over x factorial. I did tell you that basically somehow in the case when n tends to large and p tends to small, this lambda can be related with this np. So I will just conclude my today's class by saying binomial distribution, which is the two parameter distribution, under this n tends to infinity and p tends to 0, and this np such that becomes small but finite, this guy becomes Poisson distribution with one parameter, and that relation between the two turns out to be something like this. Fine. While doing that, of course, we also figured out how to take care of the expectation value. The expectation value is related with mean, how to take care of the expectation value of the Poisson and the standard deviation, so on and so forth. So in the next class, which I am going to take today, which is the additional class at 2, I will do a continuous distribution first, maybe uniform distribution, which is very useful also. And then I will take an example from the quantum mechanics to do some problem related with the expectation value of the position, the momentum for a given problem of the quantum mechanics. Fine.
Yes, sir.
Okay.
You
Yes, sir.
told just random.
Yes. Say it. Sorry, I missed. Can you repeat the question?
Actually, before 2-3 minutes, you told the name of a book. So please, can you repeat that
Oh, Glenn F. Knoll.
chapter?
Yeah, I mean, this is, I guess, your nuclear physics teacher will tell you this. This is the author, Knoll's book, famous book on the radiation. And most likely your chapter 3 is about counting statistics, most likely. And this is what you are supposed to read. If not chapter 3, then it may be in chapter 2. I mean, I'll just have a look at that. But yeah, I mean, this is the famous book for your nuclear physics experiments, and you are going to prepare for your Viva, I'm pretty sure, from this book. So who are taking the labs? I mean, those who are in the
Is sufficient for the probability.
say the name.
Sir, ArcFin, we are following ArcFin for the
Arfken.
probability.
Arfken.
Yes, sir, ArcFin.
Arfken. Right. See, the way it is, all the things which we are doing, they are there. It is just that the enough numerical problems are not there beyond this. Fine. So I would suggest that go for some book. Again, I mean, you can rely back on your Shom series. However, for the problems. However, remember that it is about the concept. Once the concept becomes clear to you, then it is the question of applying that concept in a particular situation. Right. So now you know a trick to take care of the discrete one. But in the case of continuous one, it is most likely it is the integral which you are supposed to solve, and you should be able to solve certain integrals. I mean, that's what the idea would be, I personally say. But yeah, okay. I mean, use Arfken, sure. Arfken is fine enough for the knowledge related with what we are doing up to this point. In case if there is something else which is not there in the Arfken, I will let you know. But I mean, which other book, Balakrishnan, you are having a look at it or not yet?
Yes, sir. I tried to follow it, but
Yeah,
the maths is a bit
Balakrishnan
tough.
book is scattered. Balakrishnan book is scattered. It does not follow a conventional style of the mathematical physics book. But let me tell you, at least for those students who may not have encountered anything with the Balakrishnan, the Balakrishnan is considered one of said. No, oh, your time.
Really bad for the problem solving, as far
Yeah,
as we
Shom
have got.
series, but random variable one. I mean, there are two books. One is probability and statistics, but that's not the one which I am talking about. There is a book by Shom series on random variable and stochastic processes. I most likely something like this. This is the book which you will have to look at for the problems. This is the Shom series one. Yeah, okay. The way what I was trying to tell about the Balakrishnan book is that Professor Balakrishnan is considered one of the, I would say, the foremost teachers of mathematical physics from India. He has this knack of explaining things very nicely. It of course is true that he has knowledge of advanced quantum field theory, and hence at times it's difficult to follow for certain sections. But those who may have seen the lectures of Balakrishnan, they will understand why Balakrishnan sir has written a book like this in the mathematical physics with this scattered nature, because whole idea of the Balakrishnan is to relate it with the way physics is done. and it is not entirely done in the manner in which it is done in the mathematical physics books. I mean, the Hopkins and this one. So he has come up with this style of writing it. But yes, I mean, you have some trouble figuring out which sections we should see for probability statistics. Even the linear algebra, the infinite dimensional spaces are given at some other place, whereas the finite dimensional spaces are given at some other place. So in some of you, if they are following Balakrishnan, they can just write to me in the chat box and I can just tell you which chapters to especially look at, particularly in case if you are following this book. Otherwise, also I can say it. I mean, maybe in the extra class I can discuss about it. But yes, I mean, somehow you can write to me in the chat box whenever you are following a book, so that you can see that what we are doing in the class at least has correlation with what we are doing there, whatever you are doing. So Shom series, random variable, stochastic process, fine. Of course, null is mainly for the nuclear physics experiment. But yeah, I mean, those of you who are reading it, they can read it. Okay, bye guys. The next teacher may be waiting. I do not want to take the time. So we'll
Thank you,
meet
sir.
at, yeah, we'll meet at 2.
Thank you, sir.